Thank you all so much for joining us for our second NSSC webinar of this year. Today we welcome Dr. Stephan Friedrich, who is the Cryogenic Detector Group Leader at Lawrence Livermore National Laboratory, as well as the Nuclear Science and Security Consortium's point of contact at Livermore Lab. His talk today will focus on his research on cryogenic ultra-high energy resolution gamma detection for scientific and safeguards applications. He will also discuss possible dissertation projects related to his research for any interested students. Please ensure that you have downloaded the plugin. You should have been prompted by the BlueJeans system when you logged in. If you have problems seeing the screen or have any questions for Dr. Friedrich, please type your question or any concerns in the window using the small dialog box button on the BlueJeans screen. Thank you so much for joining us. Here's Dr. Friedrich.
Thanks for the introduction, Erica. Appreciate it. So my name is Stephan Friedrich, and I run a small group at the Lawrence Livermore Lab. And what we do at Livermore is we develop detectors that operate at incredibly low temperatures. It's actually a technically quite challenging technology because there are lots of different things that come together, not only the low temperatures, but also the new detector technologies and specialized readout and all these things. Since we're a small group, we could not do this by ourselves, so we are collaborating with whoever has some of the interesting technology and is willing to work with us. That in this case includes the University of California, Berkeley. We've had a grad student, Cameron Bates, who's been with us for several years and did his PhD on this project. So the data that I'll show today are mostly part of his thesis research. So that might be of interest for those of you who want to know what kind of theses people are actually doing in my group. We're also working with the group of Professor Christian Enz. He's at the University of Heidelberg, and he is probably the world's leader in the field of the gamma detectors that I will talk about today. So it's always good to learn from the best. So we're glad that he's on board. But unfortunately, he's in Germany, and we would actually very much like to introduce this technology in the United States as well. So for that reason, we are working with Steve Boyd at the University of New Mexico on fabricating detectors of this type here in the US. So the first question that always comes up when I give a talk like this is, why would anyone want to build detectors that you have to cool down to temperatures close to absolute zero before you can use them? Why such a complicated thing? And in analogy to the answer of what makes a house a good house, the three reasons are location, location, location. And the cryogenic detectors, the same rule is what makes a cryogenic detector a good detector. It's energy resolution, and energy resolution. So you can look at the spectrum that I'm showing. It's a spectrum of a mixed isotope uranium sample. It is left over from some casting process that our colleagues at Savannah River have performed, and they get these little uranium scrapes and they want to find out what the exact isotopic composition of their uranium is. And so what I'm showing you here is a spectrum of the same source taken with two types of detectors, the coaxial germanium detector and the high resolution lead germanium detector are probably detectors that you're familiar with. That is what sort of standard state of the art currently can provide you with. And the lowest spectrum in red is from an earlier project of ours with a superconducting detector operating at 100 millikelvin. And you can see right away how many more lines you can detect from this sample if you improve your energy resolution. Turns out that there's actually two reasons why you can see more lines. One is that you have a better energy resolution that makes the peaks stick out above the background. And the second is that your Compton background itself is much lower in the detectors that we are developing. So a lot of these lines that you couldn't see and will never be able to see with the germanium detector show up just fine with a cryogenic detector. And what this allows you to do, it allows you to do accurate non-destructive analysis. You can measure your isotopic composition, and you can do this in cases where other detectors are limited by line overlap problems. And so these cryogenic detectors with these incredibly low operating temperatures, they allow you to characterize samples that you haven't been able to characterize before. And so that obviously opens up all kinds of opportunities, both from a practical point of view for nuclear analysis and from a scientific point of view. Now, just to put this a little bit into perspective, the idea that you need to go to low temperatures to improve your energy resolution should actually not be that strange to most of you. I assume most of you are familiar with some of the detector technologies that are currently being used. The gas detectors and the scintillators, they have been around for a long time, and they're still being used for some applications. And because they're large and very efficient, and particularly for search applications, they're great detectors. But if you want high energy resolution, since the 1970s, the technology of choice was basically germanium detectors. And the reason for that is you can get a much higher energy resolution with a germanium detector than you could ever get with a scintillator. And the reason for that is, most of you will probably be familiar with that too, is that the energy gap in germanium is so much smaller than it is in gas detectors and scintillators. So that means that for a radiation of a certain energy, you generate significantly more charge carriers in a germanium detector than in a scintillator, and that allows you to improve your energy resolution. And these cryogenic detectors that I'll be talking about today, they follow basically the same train of thought. They just push it to the very limit. They go to much, much lower operating temperatures so that you can further improve the resolution of your detector beyond what germanium can get you. And for those of you who remember their radiation detection course, you probably remember that people would talk about this quantity epsilon that you can see in the last column here. It is the energy that is required to generate a single signal carrier. And so if you just look at this little derivation here at the bottom of the page, if you have an energy if you have your radiation with an energy E, and this is absorbed in your detector, you create E divided by epsilon, some number n of signal carriers. These could be electron-ion pairs, these could be scintillation photons, these could be excess charges in your germanium detector. If you have n signal carriers, then the fluctuation in that number is square root of n, at least for Poisson distribution. I know there's some smart asses in the audience that will realize that there's actually correction for this, but we're not going to talk about this right now. So you have n signal carriers, you have square root of n noise. So that means your energy resolution, which is basically the signal divided by the noise, scales like the square root of the number of signal carriers down here, which in turn scales like 1 over E. So that means if you want higher energy resolution, you're pushed in the direction of exploiting some effects where you have a very small energy gap so that you can excite a large number of signal carriers for a given energy. And that pushes you into low temperature operation, because for the same reason that it pushes you for low temperature operation with germanium detectors. Now, you need the low temperatures because otherwise you have thermal excitation from your conduction band in your valence band, and that gives you noise. And if you want to suppress that noise, you've got to go to, say, 77 Kelvin so that you don't have any thermal excitations. You now make the gap even lower. You need to go to correspondingly lower temperatures so that you have fewer thermal excitation that would give you noise. So the different detector technologies that people are using nowadays, they are in some sense very similar. You have some incident particle with a certain energy E, and that excites certain non-equilibrium excitations in your detector that you can read out. If you look at the first row from semiconductors, you should be familiar with that. The energy of the incoming particle is translated into some excess charge, and the number of charge carriers that you can get depends on the energy gap in your semiconductor. And for semiconductors, this gap is typically of order 1 eV. Now, if you go to lower temperatures, you can use exactly the same principle, namely to use the incoming energy of the radiation and convert it into some excess charge. Except when you use a superconductor, your gap is significantly smaller than in a semiconductor. In a superconductor, there's also a gap, but this gap is of order 1 millivolt. So it's a factor 1,000 smaller than in a semiconductor. So with the same energy, you generate a factor 1,000 more signal charges. So you improve your energy resolution by a factor, square root of 1,000. And if you want to go even further, then you can go to thermal detectors, basically very, very sensitive thermometers. And these are the cryogenic detectors that I'll be focusing about today. Thermal detectors, they basically convert the energy of the incoming radiation into some temperature. And then the change in temperature produces the change in some quantity that you can measure. That could either be a resistance or it could be a magnetization. The detectors that we're currently developing and that will be the focus of this talk today are so-called magnetic calorimeters. So what are those? Most of you remember probably from your undergraduate days, there was something called the Zeeman effect. When you have a material that has spins, you apply an external magnetic field, there's a splitting between the energy level. It's shown down here in this graph. And the energy of these levels is different depending whether you have a spin up or a spin down particle. And if you're at sufficiently low temperatures that kT is smaller than the spin splitting, what you will have that is the low energy state is going to be occupied and the high energy state is going to be empty. So what you have in these magnetic calorimeters, you literally have a band gap that you can tune by applying a magnetic field. At zero field, you have no, the spin up and spin down particles have exactly the same energy, so no band gap. You apply a magnetic field, there's going to be the degeneracy between the two states is lifted, and you have a difference between the spin down and spin up energy states. And this difference can be of order a few microelectron volts. So when a particle comes in, you can create a huge number of excitations when you promote electrons from this lower energy spin down state into the higher energy spin up state. So that produces a change in magnetization, and that is something that you can read out. And this is just one type of detector technology that operates at low temperatures. There are actually several others. They will not be part of this conversation, but you'll probably come across them when you talk to people who do sort of some of the state-of-the-art experiments in radiation detection nowadays. So for example, there are people that you may have heard of that use these kind of detectors for dark matter searches or for astrophysics. They're used for neutrino physics and nuclear analysis, all kinds of different experiments that you can do because these detectors have a resolution that you couldn't attain any other way. So let me briefly show you a little bit what all these detectors, these cryogenic calorimeter detectors, have in common. Now how do they work? So the basic idea is that these detectors are really small, really sensitive thermometers. They're so sensitive that they can measure the temperature increase from the absorption of a single particle. It could be a gamma, could be an alpha, could be an optical photon. So they consist basically of an absorber, any absorber that is appropriate for the type of radiation that you want to absorb. And this absorber has some thermometer attached to it, some form of thermometer. And both absorber and thermometer are coupled to your cryostat at some base temperature through some weak thermal link. What I mean by weak thermal link is it is a thermal connection that allows this absorber to change its temperature relative to the cryostat. But once it has changed its temperature, it will then actually cool back down to the cryostat base temperature through this thermal link. So the thermal link cannot be too weak, otherwise it wouldn't cool down. It cannot be too strong, otherwise you couldn't heat up the absorber above the ambient temperature of your cryostat. Well, radiation comes in, say some radiation of energy E. It gets absorbed here in the absorber, which has some heat capacity C. And what this does, it changes the temperature of your absorber by some amplitude that is proportional to the energy of the incoming radiation, E over C. And then you measure this change in amplitude, and then both absorber and the thermometer cool back down through the cryostat base temperature that you started at, with some characteristic time constant of that's given by C over G. It's basically the same type of time constant that you know from electronic circuits. It's the RC time constant of a thermal circuit. And when you look at this, you're really measuring sort of microkelvin temperature increases. You're operating at 100 millikelvin, and then you make your detector small, and you're making your thermometer very sensitive. You can literally observe microkelvin temperature increases with an accuracy of a few nanokelvin. You can then go through some derivation to figure out what the actual energy resolution of such a device is, because there's always some fluctuation in the system. And it turns out your energy resolution depends on the absolute temperature T and the heat capacity of your absorber. So if you want to make this energy resolution, this number, really small, you got to keep the temperature really low. And you can't make each pixel particularly big, because the bigger you make it, the bigger the heat capacity. So for the kind of nuclear analysis, that what we want to do is we want to build detectors that have a resolution between 50 and 100 eV for width half maximum, and that sets roughly the temperature at which we need to operate, which is somewhere below 100 millikelvin, and that sets the heat capacity of our detectors and therefore the size. And so there's some trade-off. If you want higher efficiency and you need to make your detector bigger, then you lose some energy resolution because your heat capacity goes up. At the same time, you can then compensate for that by going to lower temperature up to some limit. So in the detector design in this field, there's a certain trade-off between energy resolution, which scales with the square root of heat capacity, with efficiency, and with speed. And so for the highest resolution, we need the lowest temperature and a small volume. I mentioned before that we're going for energy resolutions of order 50 eV for width half maximum, because that's what we need for nuclear analysis. Just to put things into context, the NASA guys, our colleagues at NASA Goddard, they are trying to build detectors, or they're building detectors with an energy resolution of 2 eV at 6 kilovolts, because they want to use these detectors for X-ray astrophysics, and they need a resolution of 2 eV, but they can make the detectors much smaller, so they don't need as high heat capacity, and that's why these numbers work out. The magnetic detectors that I talk about today, they basically consist of a sensor that consists of erbium dopants inside gold. So it's a golden sensor with a small number of erbium dopants in there. And it turns out that at very low temperatures, the erbium behaves like a spin-half system. So there are two levels, one spin up, one spin down. And if you keep your temperature sufficiently low, you can basically have the most of the lower energy states occupied and the higher energy states empty. When a gamma ray comes in, heats up your sensor, and that promotes some of these spins into the higher energy state, and that obviously flips the spin around and it changes the magnetization. And that change in magnetization we can read out with a so-called SQUID preamplifier. It's a very specialized superconducting magnetometer that, thank God, is by now commercially available, so we don't have to build those ourselves anymore. So what you do is you put your magnetometer into a pickup loop, and any change in magnetization produces a change at the input of your SQUID preamplifier, and that you can measure because the SQUID amplifies it and gives you an output voltage. And what you use for this kind of detector is simply the Zeeman effect that I hope most of you are familiar with. And what it allows you to do, as I said before, it allows you to exploit a tunable energy gap between the two states that you can simply dial in by changing the magnetic field. So Now, why are these MMCs so nice for the kind of applications that we are pursuing? And one of the great advantages of MMCs over other cryogenic detectors is that they do not have any resistors or any bias currents associated with them. The problem with resistors is that any resistor at any finite temperature has some Johnson noise. There's always some finite fluctuation in any noisy detector, but an MMC, a magnetic detector, does not have any resistors in it. It's just the two spin states. There's no bias current that is required. There's no resistor that's required. So you have a very, very low level of white noise in your system. And it is still there from the preamplifier, but the detector itself has literally no thermal noise. And that allows you to actually make this detector very large. If you go through the full analysis, you end up with this particular equation. And it turns out you can design your detector in such a fashion that you can make this quantity well below 100 eV for a gamma ray detector. And the kind of materials that we use, as I said before, this is gold doped with erbium, because erbium has a nice spin half system that you can see here in this plot on the right, where you look at the susceptibility as a function of temperature. Those of you who've taken your physics introductory course and not forgotten everything will remember that the Curie law says that your susceptibility should go like 1 over T. Exactly what you see here. When you plot susceptibility as a function of temperature on a log scale, you basically get a line with a slope of -1, corresponding to a 1 over T correspondence. That is just what you would predict according to the Curie theory, but we also know that at very low temperatures where quantum effects come in, you'll have deviations from the Curie law, and that's what you see here. At very low temperatures, when you're at the 1 millikelvin range, then you'll actually start these spins start to interact to the point that they will form a lattice, and they will form a paramagnetic lattice and will no longer flip that easily. So you can't operate super low in temperature because then you have spin ordering. You want to operate here somewhere in the 10 to 20, few tens of millikelvin range. And turns out, by the way, just in case people are wondering, the reason why we're working with erbium doped gold is, well, there's good reasons to work with this, but one of the main reasons is that people had a lot of experience with this material and they knew it was going to work. Turns out there are actually some theoretical arguments that you can make that other materials might work better. And so while we are currently working with gold erbium sensors, silver erbium might be better because of some nuclear effects that affect gold and don't affect silver. So that is currently one of the things that our colleagues at the University of New Mexico are working on. They're trying to develop a new material system so that we can further improve the quality of these detectors. So this is roughly what these detectors look in practice. They consist of an absorber. There's a sensor underneath that changes its spins. And then there's a coil underneath this sensor that picks up the change in magnetization and couples this change in magnetization to your squid preamplifier. The big deal for these particular detectors that Cameron, the Berkeley grad student, did in his thesis was we wanted to change the design a little bit, where we no longer put the absorber directly onto the gold erbium, but we put some posts on there, basically thin posts, so that the absorber is no longer directly making contact with the gold erbium sensor. And the reason for that is, if you want to make sure that the heat is distributed evenly in the absorber before it heats the detector. So when you have these posts in the design, you can have an absorption here in the gold absorber. The heat spreads out evenly through the absorber before it will actually heat the sensor. And that reduces the spatial variabilities in the response, so you get a higher energy resolution and a better homogeneity of your response. So in order to do that, we actually sent Cameron to Heidelberg, to our collaborators, and what he was doing there spent basically a few months there to develop a process with which you could actually make these posts and then deposit a thick absorber on them. And so this here is the product of his hard labor. This is an array of 1 to 8 of these magnetic sensors. You can see the nice gold absorbers here, roughly 200 micron thick, which by magnetic microcalorimeter standards is actually a pretty thick absorber. The sensor is underneath. You can't see it right now. You can see there are some structures here that are used to apply the magnetic field and to read out the devices. So this is what these detectors look like. 250 micron thick absorbers on posts on the gold erbium sensor underneath. Now we're very lucky that we have the guys in Heidelberg working with us, because they already have a nice setup where you can test those detectors. 20, 30 years ago, it was actually still quite a challenge to cool things down to these ultra-low millikelvin temperatures. That is one of the things that has improved very much in the last 10, 20 years, because people have started to build very specialized refrigerators that you can cool down without using any liquid nitrogen or liquid helium. Most of you will know that for nitrogen, you used to have to use, for germanium detectors, you used to use liquid nitrogen. Many of the devices still do use liquid nitrogen, but there are now other detectors available where the cooling is done by a mechanical cooler. Most typical in our field are the so-called pulse tube coolers. These are basically expansion, contraction coolers that use helium gas to cool to the low temperatures. Can't quite get to 100 millikelvin with that, but you can get to 3-4 Kelvin with that kind of technique. And then there is a different type of cooling. It uses a mixture of helium-3 and helium-4, so-called dilution refrigerators, that will then cool the detector from the 3 to 4 Kelvin to a base temperature of 15 millikelvin. So this is what one of these detectors looks from the outside. It's roughly the size of a very fat human. This is what it looks on the inside. Lots of cryogenic engineering, lots of gold plating so that you have good thermal contact, lots of copper braids and all the signal wires. So there's some quite substantial cryogenic engineering involved, but we're in the lucky situation that we no longer have to do this ourselves, because there are now companies that will sell you one of these things. Not cheap, but they work quite reliably. And then inside these refrigerators here at the base plate, at a temperature of 10 millikelvin, there's the little holder with a detector, and behind the holder here, behind some LED aperture, that's where we place the detector. And the cool down of these detectors is literally automated. It takes 24 hours. You push a button, go have some sleep, and then the next day or on Monday morning, the detector is cold. And that's what you can get with one of these detectors. Here's the first test that we did with these devices in Heidelberg. Of course, it's a little bit cheating, because those guys have 20 years of experience with these type detectors. They had, of course, set up their refrigerator in a screened room, and it was already optimized and all these things. But if you do that, you can get a beautiful high-resolution spectrum of, in this case, 46 eV from your americium source, if you operate these kind of things at about 15 millikelvin. And you can see that it resolves all kinds of lines that you would never see or would not, or would certainly not resolve with any other detector technology other than the cryogenic ones. So that was great. So that means that the detectors work. Problem, of course, is that at Livermore, we don't have quite the same nice detectors, refrigerators yet. Our detectors only use a different type of cooling technology, magnetic cooling. But for the first test run of these detectors, that was actually just fine, because we needed to make sure that we can actually get these detectors to work at least half as well as the guys in Heidelberg can. Because once you're at 45 millikelvin, or with the improved version at 35 millikelvin, they just don't have as high a signal, because the Curie susceptibility does drop like 1/T as you go to higher temperatures. So that's sufficient for the first experiments. but probably not in the long run. I'm showing this picture mostly to show you what the kind of stuff is that we build at Livermore, and just to give those students who are interested in this kind of work the sense of the kind of engineering that is involved to make these detectors work. One of the things that I haven't talked about so far is, why should the guys in nuclear engineering care about these high-resolution detectors? There may be some good science, fundamental physics involved in this, but are there actually some engineering applications? And yeah, oh, absolutely there are. So here's just the one application that we picked for Cameron. It has to do with plutonium-242. Most of you know that operation of a nuclear reactor will produce all the heavy isotopes of plutonium by neutron absorption in uranium. And the longer you keep your uranium in your reactor, the more of the heavier plutonium isotopes you will produce. So typically, when you have some high burn-up fuel, you end up with the isotopes from plutonium-238, 239, all the way up to plutonium-242. If you then are in a safeguard situation where you want to make sure that you understand that you can monitor the amount of plutonium that is in certain materials, you want to make sure that you understand all the composition of the entire composition and the total plutonium concentration in your material. Now, if you have small amounts of spent fuel, that's not as big a deal. But nowadays, the Japanese have started to build a reprocessing facility in Rokasho. Probably some of you have heard about this, where they expect to have 8 tons of plutonium per year in solution. That's 8 tons of just plutonium. The total amount of material is much higher than that. Total amount of plutonium is 8 tons. So if you are off by only 1% in determining how much plutonium is in your sample, that corresponds to an error of 10 significant quantities, meaning 10 quantities that are sufficient in theory to build a nuclear weapon. Now, obviously, that is unacceptable. So Rokasho is being pushed very hard to do very accurate accounting of the amount of plutonium that you have in their plant to make sure that nothing gets lost. And the problem with these is that of the 5 isotopes that you have for plutonium, only 4 of them you can actually see in a germanium detector. What I'm showing you here on the right-hand side is a spectrum of some mixed isotope plutonium samples, and you see all kinds of different lines. But plutonium-242 is a problem because it has only 3 lines. They are very, very weak, and all lines are very close to a much stronger line that will dominate it. So in this case, the strongest plutonium-242 line is at 44.9 kilovolt. It's very close, about 300 eV from a much stronger plutonium-240 line, and you'll have a very hard time. It's basically impossible to detect small amounts of plutonium in the presence of this large plutonium-240 line. What this forces the guys in Rokasho to do is to make extensive destructive analysis with mass spectrometry, and that's, of course, is really costly. It takes a long time, occupies a huge fraction of the IAEA budget, and it would be very nice if you could actually replace the kind of destructive analysis that is costly and time-consuming with more typical non-destructive analysis with a high-resolution detector. So here's the propaganda picture from Cameron's thesis. This is the same. This is a spectrum of the same material. Again, the same spectrum from the germanium detector in red, but this time in comparison with the magnetic microcalorimeter detector in green. The sample, as before, is a weapons-grade plutonium that we mixed some plutonium-242 into, and these spectra were taken with a 2-pixel MMC at Livermore with a temperature of 35 millikelvin. And you can see very clearly there's a much higher resolution, and you can resolve different lines much better than you have been in the past. So the one thing that we actually care about is hard to see. It's this particular line. This is a plutonium-242 line that you see right next to the plutonium-240 line. It is this particular line that we care about because it's the error in this isotope that sets the accuracy of your total isotope, of your total plutonium measurement in Rokasho. So let's just zoom into this region a little bit more to see what we can do when we want to analyze this. Here's this region again, the spectrum with the 3 lines in germanium detector, and here with a MMC detector. We can now use the intensity of this plutonium line to extract the plutonium composition. So the first thing that we try to do is there are various well-defined analysis programs that people use to relate the intensity of those lines to the isotopic abundance of a certain isotope in your sample. Turns out that the most commonly used program for this, it's called FRAM. It's made by Los Alamos. There's a similar one to MGA called MGA, made by Livermore. Turns out that the conventional programs are actually currently not that well suited for this because they all assume that you're using a germanium detector. And when you have a germanium detector, you cannot calibrate the energy efficiency very well just because germanium has a different absorption efficiency as a function of energy than gold does. So what Cameron had to do, he basically had to come up with his own analysis routine where you could implement a gold absorber and replace the FRAM code with his own analysis code. And if you want to do that, so one of the things that you're actually very lucky in, you can see here in this spectrum, there's a whole bunch of different lines from the plutonium-239 isotope all over. And the energies and the intensities, the branching ratios for these isotopes are very well known. So you can use those branching ratios and the measured intensities to calibrate your energy resolution as a function of energy. And that's what we've done here with the green curve. And then you can use this to extract the total amount of plutonium in here. And what we get is we get about 11% plus minus 0.43% of plutonium-242. And that agrees within the error bar with the mass spec data that we've done on the same sample. So we're at the point where we can start to do quantitative analysis with these detectors in cases where germanium is limited by line overlap. 2 things I want to point out. First of all, cryogenic detectors will never replace germanium. Now, the germanium guys don't have to be worried. These detectors they're going to augment what you can do with germanium, but germanium is so much simpler to use that it also so much better at high energies that I don't think you will replace germanium ever. But what they can do, they can augment the germanium detectors in cases where you have line overlap problems. That's very similar to what people do nowadays for the high energies. People typically use a coaxial germanium detector that has high efficiency at the high gamma ray energies. The low energies use what they call a LEPS, a low energy photon spectrometer germanium detector. You have a lower efficiency, but you have higher resolution, and that is preferable at low energies. In the same way, I imagine that this is something that we would like to do with these detectors as well. Except, so far, we're actually still limited by the statistics in these lines. These are comparably weak lines, and with just 2 small pixels, you just don't get enough counts. So one of the next things that's definitely on our to-do list, we want to do arrays so that we can get higher efficiency. So I've given you an overview of what we do with our cryogenic detectors, but also showed you where the limitations are to give you a sense of what's next. So obviously the performance of the detectors was better in Heidelberg than it was at Livermore, and that was simply because they have a refrigerator that goes down to a lower temperature. So for higher energy resolution, it's quite simple. We're going to replace our current ADR refrigerators with dilution refrigerators. And we're very lucky that the guys at Blue Force will sell us one, provided that we can convince DOE that we can get the funding for this. So there's still going to be some cryogenic engineering involved, but the vast majority of the work is actually done these days by commercial companies. We need to improve the detector designs for higher speed. Currently counting at a few counts a second, because there's various imperfections in the current detector designs that doesn't allow us to count faster. We definitely want to go up to, say, 100 counts a second per pixel. Now, that's slow by scintillator standards, but by cryogenic detector standards, that's actually acceptable, because you can extract quite a lot more if you have high resolution and you don't need as many counts as you do in germanium detector. So that requires new photolithography, and that's probably going to be done at Heidelberg. And if students are interested in this, again, Cameron went to Heidelberg for a while to work with them and learn all about detector fab. This is certainly an option again. Because what we really need to do is we need to make small arrays, so that we no longer have just 2 pixels, that we have at least 32 or maybe 64 of those pixels. And then you could greatly improve the number of counts that you would get, and you would very much get higher sensitivity so that you could analyze weaker sources. That then would require improved electronics, but we know how to do that. One thing that's on our mind is, can we actually replace our current sensors with the silver erbium sensors? That's something that the guys at the University of New Mexico are currently working on. And we all hope that our collaboration is going to be successful, that we can eventually transfer this into the commercial industry, because it would be very desirable if these kind of instruments are available for sale. And we're working with a small company in New Mexico called Star Cryoelectronics. It's a company that we have commercialized other cryogenic detectors with before, and that has worked out very nicely. Now, these magnetic calorimeters are a little bit younger, so they're not as mature, they're not quite ready for commercialization, but sooner or later I think it would be very desirable if we could have a commercial source of these detectors in the US. And then, of course, when you have a new detector like this, you want to be able to use it for some interesting analysis, and there's all kinds of applications, both in for more practical applications and safeguards, or in scientific applications to look at certain lines that you could never detect with other detectors. So the entire field is actually quite interesting, and it's growing right now, and there are several quite diverse thesis projects in it. Most likely, future students would do exactly the same thing that Cameron would do, namely a little bit of both, a little bit of cryogenic engineering, a little bit of photolithographic detector fabrication, work on the electronics, and then do some nuclear analysis with these detectors. So let me summarize. We're building magnetic MMC gamma detectors. They have very, very high energy resolution, and they're based on measuring charges and magnetization in a magnetic sample at incredibly low temperatures, close to absolute zero. What we've currently measured, we have measured an energy resolution of 46 eV, so a factor 100 or so, a factor 10 or so better than what the statistics limited germanium detectors will get you. But the price that you pay is that you go to very low temperatures and that you have very small pixels. At Livermore, the resolution is currently a little bit lower, but that's because we don't have the fancy new refrigerator yet. But these data should be good enough to convince everyone that should give us a lot more money to expand this to higher resolution in the future. And the detectors are very linear and very reproducible, which is great, because you need linearity and reproducibility, because you want to ultimately add spectra for many different pixels, because one pixel is so small. So for good statistics, you just need more pixels than that. It's essential that the detector is very linear and that you can add different pixels from different cooldowns. So we're lucky. The design has worked out. That part of the design has worked out very well on the first attempt. What has not worked out so far so well is the speed. It's still too low, so we're working on newer geometries and on arrays and on resolution. But that's going to be the project for the next student. Cameron has just accepted a position at Los Alamos, so he's going to leave us, and the project is open for anyone else who would be interested in joining us. Thank you very much.